Hi everybody, and welcome back to Mathematical Misconceptions. Today we're going to be talking about a common mistake I see when factoring the sum of perfect squares and how people associate it to be the conjugate pairs, and that's not necessarily true. What I see a lot of times is that people mix up this over here with the sum of perfect squares with something else, which is far more common, and especially with Algebra 1 students and above. In Algebra 2, this is where you get into the sum of perfect squares, and you have to factor it a little bit differently compared to what we see on the right-hand side. So if we're ready to explore this mistake, let's dive in. In order to prove that these two are in fact not the same, we could start by plugging in numbers, right? Let's just choose easy numbers. Let's say A is equal to 2, and B is equal to -1. I always say if you can choose negative numbers, that's great, because you'll instantly see that in some cases, the left-hand side will not be the same as the right-hand side when it comes to the sign of the final number. Let's see if that's true in this case. All right, so we have A squared, so we have 2 squared plus -1 fully squared. Put that -1 in parentheses so you know to square it. Does not equal, and then in this case it's going to be 2 plus -1 times 2 minus -1. So we'll fix those signs in a minute. Okay, so 2 squared is 4, and -1 squared is +1 plus 1. Does not equal. And then in this case, it's going to be 2 plus -1, which is just going to be 1. So it's 2 minus 1, right? Times. And then 2 minus -1 is going to give us 3. So 1 times 3. And in fact, we can see right here that 5 does not equal 3. If you're doing a test and you're not sure you factored something correctly, just choose easy numbers. And that'll verify it for yourself. And that'll give you a tip that, maybe you should factor this a little bit differently. So that's a numeric example that we see right here when we plug in 2 and -1. So it begs the question, what does this right-hand side actually represent? And what we're going to do is we are actually going to manipulate the right-hand side through FOIL. I'm going to go ahead and erase the numbers, but if you're writing this down, feel free to pause the video right now and write this down, and then rejoin me when you're ready. I'm going to go ahead and erase it. In the next part, we're going to go ahead and FOIL the right-hand side. And we're going to see the right-hand side is going to look a little similar to the left-hand side, but there's going to be one fundamental thing that is different. Let's go ahead and FOIL. A times A is A squared. FOIL, first, outer, inner, last, just as a reminder. Outer, A times -B is minus AB. Inner, B times A is plus AB. You can change the order. BA, AB, doesn't matter, it's multiplication. And B times -B is minus B squared. Now, when we multiply conjugate pairs, what is the shortcut we can use? Well, the inner and outer always cancel, and that's the beauty of it. So this is not equal, and once again, we can say that A squared plus B squared does not equal A squared minus B squared. So in the original right-hand side, what did we actually start with? We had conjugate real pairs, so that gives us the difference of perfect squares. It's not the sum of perfect squares. These two are not, in fact, the same. Now, you can make the argument, well, what if B is 0? Yeah, that's an exception, not an identity. And we are trying to create identities here that work for all real numbers. So be careful. Do not let the exception be the rule. All right, so how do we verify that this is true? How do we verify that this is true? Well, we can set A plus B times A minus B equal to A squared minus B squared. Plug in some numbers. You can choose 2 and -1 again, and you'll see that it in fact works each and every time. But the real question is, what does the left-hand side factor as when we have the sum of perfect squares? This is a definition we often have to accept within algebra because it's really hard to derive this. So this is a definition you just need to roll along with. So A squared plus B squared does in fact factor to A plus BI times A minus BI. And as a reminder, I is defined as the square root of -1. One of the things you can remember is that when you're factoring it, it looks very similar to the top, a plus b times a minus b. But because we have a plus, you can just imagine taking that I out of the plus and putting it right there. That's a little mnemonic trick that you can probably try for yourself. Let's verify, though, that the left-hand side is equal to the right-hand side. We're not going to plug in numbers. We're just going to do straight algebra. Let's FOIL the right-hand side. All right, so we have a times a is a squared. Outers, a times negative bi is minus abi. Keep things in alphabetical order. And then bi times a is plus abi. And then bi times negative bi is minus b squared I squared. Now, you'll notice this follows a similar rule as above. When we multiply conjugate pairs, by the way, conjugate means that we have same terms, different signs when we're multiplying. The middle terms here, even though we have imaginary numbers, they still cancel to 0. So we don't have to bother with them. All right, so we have a squared right here on the right-hand side. And then we have this minus right here. And you're thinking, well, is it going to be a squared minus b squared? No, because what does I squared define as? If I is equal to the square root of negative 1, let's just square both sides. I squared equals negative 1 by definition. You may be tempted to just plug in negative 1 right here, change the sign as you go along. If you're good at that, that's great. But I encourage students to show more steps because it increases your accuracy. And when you're accurate, then you can be fast. So this is going to be the same as minus b squared times negative 1 squared. And negative 1 squared is, of course, oh, sorry, that's not negative 1 squared. It's just negative 1. Be careful when you're plugging things in. Negative 1 times a negative is positive. So in fact, this is going to be the same as a squared plus b squared. Always double check your steps. Even if you're a professional at this, it's always good to double check your work along the way to make sure what you're presenting is accurate. Let's recap this. So we're going to recap it on this side. So we have a squared plus b squared equals a plus bi times a minus bi. And then finally, a squared minus b squared is equal to a plus b times a minus b. So the way that I like to phrase it in a way of a jingle is that the sum of perfect squares creates imaginary conjugate pairs. So it has the imaginary term, right? Whereas the difference of perfect squares creates conjugate real pairs. Real because there's no I in here. We don't have the square root of negative 1 to deal with. So once again, the sum of perfect squares creates conjugate imaginary pairs, whereas the difference of perfect squares creates conjugate real pairs. I hope that helped clears up some things, especially when you're doing homeworks where you're doing the sum of perfect squares. You may see things dressed up a little bit differently with numbers and different variables. So just be careful with that. And I hope that this helped you. This is Mathematical Misconceptions. If you have any questions on this lesson or anything else that you are facing in math, please drop a comment below. Otherwise, I will see you in the next one. Thank you.